All right, guys, I'm going to talk about something a little tricky, especially if you haven't covered it in math, which you probably haven't. I don't think it'll come up on the exam, so I'm just going to get you to work on it today. But just in case, I want to have shown it to you, just so if by some chance one of the questions involves something like this, you're not high and dry. But yeah, pretty unlikely given that your calculus class isn't expected to have finished. And this is something that barely even gets covered in that. Certainly not till towards the end. So today we're going to talk about something called separable differential equations. It's an equation where you've got something related to its derivative. And you can solve anything of that sort if it has that property. You've got kind of like a fairly direct relation between something and its derivative. So I've got an example from an old AP question involving that, and we're going to go over it. First part, it's just setting it up, making something equal to its derivative. So we've got this block of mass m with initial velocity v naught at time t equals 0, sliding on some horizontal surface, and it's got some crazy friction force that is directly dependent on its velocity, directly proportional to its velocity. Now this is not super likely for friction, but it can happen for air friction depending on how it's flowing. Anyway, so, or other drag force style things. So that's not too hard. We've got F net equals m times a, and the only horizontal force on the sucker is your drag force, your friction force here, which is minus kV, minus because it's opposite to the direction of motion. And so that's going to equal m times a. So if you want to solve for a, it's just, we just divide both sides by m. And we've got your acceleration is minus this beautiful k, v over m. So it shouldn't be too hard. F net equals ma, and our net force is just this funny drag force given to us. But acceleration is the derivative of velocity with respect to time. So really, we've got this dv dt equals minus kv over m. So this kind of form sets things up for separable differential equations. Now, the way you're generally taught that is you basically get all your v's on one side and all your other junk on the other side, and you kind of treat this like a fraction. And so we multiply dt by both sides and divide both sides by v, and you're ended up with something like this. Now that's often how it's taught, and it works great. That confused me because it didn't make a ton of sense until I thought of it more like this. So if I want to integrate both sides with respect to t, and I divide v by both sides, so it's on the same side as its derivative, notice that while I'm integrating with respect to t, dv dt next to a dt, that's a small change in v. Like this is a small change in t. This is the change in velocity that a small change in velocity that corresponds to that small change in time. And so this is basically exactly substitution. So you can either think of this whole separable differential equations thing as being like, hey, we just do some math with this dv dt. We get the dt to one side and kick all our v's, anything relating to v on the other side, and then just take the integral. And that works, and that is how you should probably do it once it makes sense to you. But to understand how it works, this is how it works. It's really just substitution, which hopefully you're familiar with. One thing that always screws me up with these things is you got to be really careful with your bounds. Right now we're starting at time equals 0 at a velocity v naught. And we're finishing at a velocity v. So if we want to know the velocity at a given time, it would be this velocity. And that time that corresponds to that velocity is that. yeah, so we're integrating over the same kind of time domain, because this change in velocity corresponds to this change in time, and this small change in velocity is equivalent to that small change in time using substitution. So hopefully you can puzzle this through. It is a lot for a day, I'm sorry, but probably not going to come up on your exam, and you'll have entire classes on this sort of thing. Anyway, once you integrate this and include the bounds, don't forget to include the bounds, so final minus initial. The integral of 1 over v is the natural log of it. So we have the natural log of v minus the natural log of v naught on this side, using our bounds. And then we have minus kt over m, because we just have this dt and the rest are constants, minus 0 when t is 0. So put those together and we're good. Remember your log rules. So some log minus another log, it's the same as 1 log. I should maybe do another step. I sort of skipped a step there for you guys. It's the same as log of v over v naught. Anyway, so if we do everything to the power of e, that'll cancel out our natural log, and we're left with v over v naught. And it puts all this to the power of the base of the natural log. We can multiply both sides by v naught, and we have our velocity formula. There is no constant, because when t equals 0, this whole natural base of the natural log term goes to 1, because anything to the power of 0 is 1. And so the whole thing ends up being v naught. So we don't need any extra constant term to deal with our initial conditions. And so that gets us part B. That's the differential equation that I really wanted to show you. But then may as well do part C as well, where you want to find the total distance. So we just integrate our velocity formula from t from 0 to infinity. Because that point for sure it's stopped completely. It's sort of a limit deal. Anyway, so if we integrate it from 0 to infinity, we end up with this lovely guy, evaluated at infinity minus evaluated at 0. Hopefully you can see why this is the integral of that. If you take the derivative of this, you will get that. And then at t equals infinity, this whole term goes to 0. So the whole thing goes to 0. So we've got 0 minus, and then the situation when t is 0. When t is 0, this little business is 1, and so we got negative mk times v naught. The two negatives cancel, and we are left with this as the total distance the thing travels before it stops. Now, this is a lot. Think it through a lot. There are resources. This is called separable differential equations. So you may want to look something like that up on Khan Academy or some other site of your choice. And let's just try to do one question today. Just so if it does come up on the exam and when you are exposed to this in the future, you're ready. Probably not coming up on the exam, but just wanted to show this to you just in case. Anyway, have a great rest of your day and have some fun with this. It is pretty interesting and very useful stuff. There's branches of math devoted to differential equations, this kind of thing. Differential just being formulas relating to their derivatives. Anyway, thanks for listening and have a great rest of your day.